It is the 1st of September, roughly in 2025, roughly 8:15 a.m., and we are continuing along Dummett and Foote 1.6 on homomorphisms and isomorphisms, going directly back to where we previously were. We mentioned a proposition which discussed the inverse of an isomorphism. So let's move on to a different proposition which discusses isomorphism invariance. So if phi which maps G to H is an isomorphism, then, well, for one thing, the order of G is equal to the order of F in the the order of H in the case of finite order. Two, camera check real quick. Good to go. 2, G is abelian. Well, if and only if H is abelian, for each x within G, the order of phi of x is equal to the order of x. So orders of elements are preserved. All right. So get 4. G is cyclic if and only if H is cyclic. More generally speaking, f with respect to a generator x is equal to the generator of phi of x. So that's an interesting little thing right there, isn't it? Very nice. Take a function, becomes an inverse. Becomes a generator. It's very nice. Okay. So let's get a look at the proof of this here in a moment. Okay. Camera check. Camera check good. So we're trying to say 4 different things, right? So let's start with the first one. So a bijection preserves cardinality. That's a more ingrained, closer to the bones sort of idea that this one builds off of. So, well, that's a less rigorous way of saying it. But a bijection preserves cardinality. So we can say that the cardinality is preserved in this case with G equal to h in terms of cardinality, in the case of finite cardinality, right? So, 2, if G is abelian, then for A and B within H, we can write that A is equal to phi of x, B is equal to phi of y. Then from this, we can say that AB is equal to phi of x, phi of y, which is equal to phi of xy, which is equal to phi of yx, which is equal to phi of y, phi of x, which is equal to b a. And then for the converse case of that, we can say that the converse follows by symmetry. Now for 3, since phi of x to the power of n is equal to phi of x, so phi of x to the power of n is equal to phi of x to the power of n. Say it differently, so that way, you know, it's like auditorially speaking, it's different. We have phi of x to the power of n is equal to the identity of h if and only if x to the power of n is equal to the identity of the group G. So, the least positive such n is the same in G and H. Least positive is the same. It's one of those trickier ones because you have to like just think about minimality, right? And so, but this here preserves it across those lines in both G and H, so sticks it firm such that the least positive such n is the same in G and H. So that holds. Now let's move on to 4. If G is equal to that which is generated by x, then the image of phi is equal to that which is generated by phi of x, which is equal to h by surjectivity. On 2. Right, so how do I say this more? I mean, it's intuitively speaking, right? So G, well, I mean, we go back to the structure of what this is, right? We go back to the structure of a homomorphism. We go back to the structure of an isomorphism. Let me check this, because I want to speak more intuitively on this, right? So it's like variant G map to H. Well, we can say that this unto relationship, this stamping from one to another, we can say that, okay, so the image of phi that equal to that which is generated by phi of x is equal to h. Like that holds up. That holds up really well by surjectivity. There's more that can be said, but I'm lacking the words. But We'll get into it for exercises, I'm sure. We'll take a more closer look at that with exercises. So, but anyhow, the equality phi of the generator x is equal to the generator, that which is generated by phi of x, follows because, and that's what this little symbol I use means, by the way, B/C means because phi of x to the power n is equal to phi of x to the power of n for all n within the integers. Yes, so you can take like iterations of this. Iterations? I don't know if that's the appropriate word. Exponentiations? Exponentiations? Maybe? Of that, but suffice to say, like you put these generators like dot to dot to dot to dot to dot, right? That doesn't really mean anything rigorously, but how would I say this? It's like you multiply this thing by itself, or like operate this thing by itself in a way, over and over and over again, and this is what this is sort of getting at. This is what that is getting at for all n within the integers. So yes. So that the equality of that follows, roughly speaking, from this, ergo it holds up. So we have our properties 4, 3, 2, 1 roughly proven in that manner. So let's go to, forgot a camera check. Forgot to check the camera. Camera's good. Erase that first part anyway. Oh well. So let's get on with orders through a homomorphism. So that's what this will roughly cover. Order divides under homomorphism. So, more specifically, let phi be a function which maps G to H, be a homomorphism, and x within G, x within the group G, have finite order. Absolute value of x is equal to n. What's the absolute value? The order of x is equal to n. Then, you know, like I'd like it if we just kind of, you know, use 3 letters and then we said, you know, x is equal to n. That would be nice. But we've already settled upon certain things, certain notational things. So it's like I mentioned earlier, the issue of using the less than or equal to sign to say that something is a subgroup of something. Well, let's just say, like, you know, just say SBG of H. Oh dang. I can see how that gets hairy. So let's just stick with the notation that we have, right? So so the order of x is equal to n. Then the least positive. Whoops! Sorry. No. I was blanking and going back to a previous line which we had already discussed for the proof previously. So let's say then the order of phi of x divides n. So, moreover, the order of phi of x is equal to n if and only if the kernel of phi intersects with that which is generated by x is equal to the set containing the identity of group G. Equivalently, if phi of that which generates x is injective. That which is generated by x is injective. Phi of that which is generated by x is injective. There we go. I think that's the proper way of saying it. So let's look at the proof to sort of think more groundly, specifically, more in detail, though still rough, an approximation of this idea. Well, let's first discuss, what is this like, right? So we were talking about in the preliminaries about this, the theorem in which we have that any composite number is divisible by primes, right? So it's sort of similar to that in terms of we have something bigger and we can divide that. But that's just sort of a rough parallel in a sense, but it doesn't hurt to show these rough parallels as we make our way to things more and more complex. So with that in mind, let's now get into the proof. So since phi of x to the power of x is equal to phi of x to the power, since phi of x to the power of n is equal to phi of x to the power of n is equal to phi of the identity of G, which is equal to the identity of H, the order M, which is equal to the order of phi of x divides n. Is that true? Let's think about that. Yeah, that's true. Okay, so that follows, and if you think back to my parallel idea, we have something similar going on here. So if phi of that which is generated by x is injective, then x to the power of k is equal to the identity of G is the only solution of phi of x to the power of k is equal to the identity of H. It's injective. So it's 1 to 1. Then x to the power of k is equal to the identity of G is the only, right? The only solution of phi of x to the power k equals equals the identity of h. So what does that imply? What does that imply for M and M? M and M. Well, he's Slim Shady, but he's also Marshall Mathers. So there's that. But anyway, M is equal to N. Hence, M is equal to N. By uniqueness, right? So implied by injectivity. That holds up. Conversely, if M is equal to N, then we have that phi of x to the power k is equal to the identity of the group H, which implies that N divides k. So x to the power of k is equal to the identity of G. Ergo, the restriction is injective. And this word, the restriction, that has a lot more theory behind it in terms of algebra. Well, yeah, in terms of everything, yes, but algebra more specifically. Because the restriction itself is a structure. So, but suffice to say, ergo the restriction is also injective. So we can have that back and forth such that the order of phi of x is equal to m if and only if the kernel of phi the intersection of the kernel of phi and that which is generated by x is equal to the identity of G. We can say all of that. We can say all of that and what lies before within this proposition without getting into the rigorous formality of what's going on with that word there. So we'll discuss that more in depth later. Now, that holds as a rough proof. So let's just leave it at that and move on to the next proposition. I forgot to do a camera check on that, but that's fine for now. So we're going to look at this sort of standard constructions and examples more in depth here. Specifically, we'll be getting into a lot of calculatives as the lecture comes to a close, but let's just look at a proposition involving composition for now. So if phi is a map from G to H, and oh no, is that the actual? What is that? Can't remember. Gosh dang it. And we have another function which maps H to K, or H to big K, to group K, are homomorphisms. Then psi? That's psi? Yeah, I think that's psi. We'll just call it psi for now. Is psi. If psi, okay, so if phi, which maps group G to H, and psi, which maps H to K, are homomorphisms, then psi composed with phi, I mean, you can see how saying phi instead of phi really works there, but maps G to K is a homomorphism. Proof of that, rough proof of that, for all x, y, for all x and y within G, we have this as the case where psi of phi of x y is equal to psi of phi of x y, which is equal to psi of phi of x phi of y, which is equal to psi of x, which is equal to psi of phi of x times operated with c psi of of phi of y, which is equal to psi composed with phi of x operated with phi of psi, of psi composed with phi, we'll just call it phi, goodness, of y. So there we go. So psi composed with phi of x operated with psi composed with phi of y. And so therein we have that this entire thing is in fact a homomorphism. Well, yes, well, this entire thing, not, well, let's just let it sit there. So there we go. Camera check. Good. Moving on to the next one. Now let's discuss inner automorphisms. Let's juxtapose the outer automorphisms. Fix G within the group G. The map let's just say the map Phi sub G, which maps G to G, defined by phi of G of x is equal to G x G inverse is an automorphism. Okay, so automorphisms are important, but it's like whenever you look at an automorphism, it's like it doesn't look like it would be important at all. But like there's entire textbooks and stuff about about this thing, and so that's a very curious thing. But we'll we'll see about what that's about. So proof. Well, phi sub G of xy is equal to G gxy G inverse. Inverse of G, which is equal to open parentheses Gx inverse of G, close parentheses, open parentheses, Gy G inverse of G, close parentheses, which is equal to phi sub G of x operated with phi of G sub y, no, phi sub G of y. So phi of G is a homomorphism. This could be proven more rigorously. That's fine. Let's hold that. It is bijective because of the invertibility with inverse phi phi sub g inverse, phi sub inverse g. Hence, it's an automorphism. Can't wait to get into the exercises where the things are more rigorous, but that holds. I'm just sort of throwing different notation at you, but you know, saying it out loud helps to make sense of it, hopefully. It's like Euler was blind to get over yourself. No, but that was until later in his career, in the same way that Beethoven was deaf later in his career. So it's an interesting parallel, and they happen at around the same time. But anyway, let's get into some calculative examples. Specifically, in this case, reduction modulo n. So, phi, which maps the integers to integers mod n, and phi of k equals, what is this, the residue class, the equivalence class of k sub n is a surjective homomorphism. So, for the kernel of phi is equal to the n integers, because modulo n integers, which is equal to the set all the way up to -2 n, n, 0, n, 2n, and you just keep going, just keep on multiplying the integers by n. So by injectivity, well, by the injectivity criterion, I guess you could say more formally, phi is injective if and only if n is equal to 1. So that's an interesting case, right? K mod n, equivalence class, residue class. I can't remember for sure which one that denotes, but I think it's equivalence class. Right. Let's get on to another calculative example. So, in this case, for determinants, so let's say we have the determinant which maps the general linear group of f to the units of f. This f being a field is a surjective homomorphism. Kernel of the determinant specific linear group, I guess you could say, of f, which is equal to the set of A within special linear group, though you know, it would make more sense to use S as specific. But I believe in this context it's called special. So, if I'm not mistaken. So, the set A within G, within the general linear group of F, such that the determinant A is equal to 1. A subgroup, comma, a subgroup of the general linear group of F. It would make more sense if you called it specific, because you have specific, general, universal, particular, right? So, oh well. Camera check. Camera's good. Moving on. Keep calm, carry on. Alright, so another calculative sign of a permutation. So let's say we have this denoting sign. We have the symmetry group plus or minus 1 is the set containing plus or minus 1 is a surjective homomorphism with kernel A sub m being the alternating group, so let's say that more together, well, more concretely, more, what is it? Specifically more robustly, more, I don't know, there's a word for it. Consolidatingly. Consolidatingly? That's not a word. Well, say sign which maps S sub n, the symmetry group, to the set plus or minus 1 is a surjective homomorphism with kernel being the alternating group. Hence, quotient group, well, let's say the symmetry group mod the alternating group, excluding the alternating group, is isomorphic to plus or minus 1. Yeah. So I make a note within my notes that the quotient group is discussed in later chapters, and we've seen this sort of thing, right? We've seen this whenever we talk about Z mod n. But you know, it's a similar sort of circumstance, which we are discussing here within this structure. Very good. Now, let's say, camera check, camera's good, moving on. To another calculative example. We talk about the orientation homomorphism on dihedral groups. So if we have phi to be a map from the integers to the integers, phi of k is equal to 3k is a homomorphism. Kernel set containing 0, singleton set 0, hence injective. So the image 3 integers 3 times integers, is not equal to the integers itself. So not surjective. Which is a strange case, right? I mean, yeah. Something that is injective but not surjective. It's very contrary to intuition. Because it's like, well, you'd think like, you know, something that's injective must be bijective, and something that's bijective must therein be both injective and surjective. But it's like, in this case, it's like, that doesn't hold true, which is interesting. So like, if you were ever asked for an example in which this is the case, you point out this, that would work. And if it's not, then feel free to correct me, but I believe that's directly from the book, if I'm not mistaken. So it's like, it's one of those things that you have to do a double take, and it's like, well, is that actually true? And we could go and prove this more rigorously, but yeah, not now. That's so. With that, I'll leave with closing remarks. The study of kernels and images foreshadows the isomorphism theorems, which we'll get into later roughly. A homomorphism from G to H factors G into its kernel and image. Formal statements and proofs require quotient groups, and these will appear in later chapters. And that's it for now in discussing homomorphisms and isomorphisms and the basics of Dummett and Foote in 1.6 for now.